Welcome everyone to our support vectors paper reading session. Today the topic that we are going to talk about is DeepSeek-OCR, context optical compression. This, surprisingly, despite OCR being in the title, has less to do with OCR and far more to do with the fundamental architecture and optimizations in the transformer. So I'll start by mentioning the core value that this paper brings. When you look at the current language models, one of the limitations is the context length. Gemini has a context length which is huge, like 2 million, but then GPT has a context length that is about 200,000 K. Most other models have context lengths that's more like 32,000 tokens. So with that in context, it has become quite common for people to send vast amounts of information in the context window along with the user prompt. So for example, some people treat the whole document they can take, an encyclopedic document, and they can feed the encyclopedic document into the LLM as and then ask a question. And when they do that, then in that case, you have a context length problem, because if the document doesn't fit into the context window, how do you deal with it? So there's a practical problem. There is another. So let's just start writing it down. And guys, let's keep it very conversation. We have a small group with this one. I think we can keep talking through this paper. So please do keep interrupting me, and that will be fun. And we'll talk our way through this. Now, so the practical problems that this paper, and the core problem that this actually is trying to solve is not OCR, but a large language models. Main problem is that context window limitation. But it puts an upper bound to how much information that you can put into a LLM, into the input. That is one. The other problem that you have is the very nature of attention, self-attention, if you remember. You have this, if you look at this equation, the classic equation for attention from the original attention is all you need. This is the main problem is this term, the quadratic term, because we are paying the quadratic penalty in compute. So for example, if you increase the token length by a factor of 10, the number of computes increases by a factor of 100. Right? It goes quadratically, and that has been always a problem. It increases latency, it increases compute costs, and so on and so forth. So this paper addresses that as the core issue. Now, if we can take care, if we can mitigate that quadratic compute, we'll have benefit. And also, what if we could take an encyclopedia whose token length, word length, would exceed that of the context window. And if you try to put that into the LLM input, you can't do that. It will get truncated. So is there a way to put that in? And this paper comes forward with a way to do that. Now, this has value beyond static documents. Quite often, conversation systems like chatbots, etc., what they do is they remember the past conversations. So, for example, when you go to ChatGPT and when you have a conversation, not only does it remember the current conversation history, quite often it is dipping into all the past conversations you have had with ChatGPT. It's dipping into memory. And all of those things now become part of, in some form or the other, part of the context window that goes to the LLM. So obviously, increasing somehow the capacity of the context window without actually increasing it is one of the big achievements or the core achievement of this paper. So how does it do it? And I'll sort of talk about the main idea, and then we'll go into the detail. What this paper posits is that, people have this saying, often people say that a picture is worth 1,000 words. Right? For example, if you want to describe in detail that the clouds were puffy in the blue sky, there was a meadow. In the meadow, there was a child there playing with her, let's say, dog, a golden retriever, that she was holding in her hand, and that there was a basket of fruit next to her, and all of that. You have used a lot of textual description to accurately describe what is there. Instead, you could just have a photograph, a snapshot of the girl in the meadow. Right? And so a picture, a photo, does speak volumes, that it will take a lot of tokens of words to describe in complete detail. Another way to say it is, a more technical way to say it is that pictures have a much higher information bandwidth. They carry far more information in a single picture than it is in words. So with that insight in place, what this paper asks, the basic question that this paper asks is this: can we go like this? You take a text with its thousands of tokens. So typically, let's say a line contains about 20 tokens. And let us say that there are about 50 lines in a page. So that makes it approximately 1,000 language tokens. Can we somehow convert it into an image? Can we convert it into an image? And so you could say, how would you convert this narrative into an image? In this paper, they say that just assume that instead of reading the words, imagine that you have just written the words on a page like this. And then what you can do is, instead of processing it with the LLM directly, what you do is you pass it through this pipeline. First thing that you do is, and so these are the stages that it says, take this image. Now for image processing, especially for encoding, we use SAM and VIT. Dead. So these are words we use. Those of you who are familiar with SAM, you know that it's a segment anything model. Basically, what SAM says is that point me to something in the picture, and I'll immediately identify, put boundaries around that picture. If you have a football, I'll put boundaries around the football. I'll create a segmentation map for that thing. That is SAM. And the VIT data, just to get your recollection, VIT was the first, VIT, if you remember, was the first paper that said images can be patchified into patches of 16 cross 16 pixels. And then these patches, they treat it as a token, a visual token. And then you feed it into, then you do whatever you do normally. For example, you can feed it into a bird-like or encoder, bidirectional encoder, which is what VIT is, basically a bird-like structure. And then you get image representation of whatever you're looking at. So that is your VIT. And I suppose most of you would remember it. Guys, feel free to ask me questions along the way if you're not familiar with something. I'll be happy to explain it. So let me just conclude this. A simple VIT would just take an image, some image, and then it would go into the VIT, and what would come out are these visual tokens, like or visual embeddings, H1, H2. Okay, and then you get contextualized vectors for each of the tokens, essentially. Right? Now, where SAM comes in is, what SAM does is it takes that and it says, okay, let's decode that. You have encoded a lot of information here. Maybe from the side, you also give some user prompt. What do you want to look at? Like point at like football, let's say football, or soccer. Let's say use the word soccer. And what you do is you train. Now there are two channels of information going in to the decoder in the SAM's decoder. You have internally a decoder, SAM, of SAM. Right? So SAM is basically an encoder decoder. So here are the visual vectors going in. Visual, and here is the prompt vector going in. Prompt tokens going in. And together, what it produces is a masked image, where the football or the soccer has been specifically highlighted. Right? So that is what SAM, most of you may have used SAM. SAM stands for segment anything model. But while the practical use of SAM is, and by the way, SAM is much better than the older architectures like UNet. So let me just say it's much better than UNet and things like that, architectures. So one question is, why does SAM work so well? And because this paper uses it. See, the reason SAM works so well is the VIT part is giving you the objectness information of what is there, what is it looking at. And then the decoder is basically using that to draw boundaries around objects. It recognizes the extent of boundaries of objects. So that is what SAM is. Now, what this paper is saying is that you can do this journey, take a large text, convert to image. An intuitive way to think of it is just write the text on a page and take a picture of the text of the page. It becomes an image. So it becomes an image, pass it through SAM, detector, VIT detector means it is basically the entire SAM, but you remove the last layer which produces the mask. You just look at the inner understanding that SAM has of the picture, of this picture, that the understanding that it has come up with. You extract that. And so then what you get is, now SAM, because it understands boundary. Now think of what is happening in a page. Suppose there's a page, is a picture, there's a picture here. There is text here, some text, and there is a chart here. Let's say that there is a chart that says something like this. The fact that SAM can identify boundaries will mean that the first thing it will do is it will recognize the boundaries of this. Okay? It will know that this is text, this is this, and this, and that there are three things on this page. And the second thing that SAM does, or you can do, is when you now, so this is it. It not only understands images, not only understands, semantically understands cats and dogs, but puts or learns their locations, learns their locations, because that's how it develops its masking ability. Locations. That's the main point of SAM. That's where it differs from basic VIT. Right? So with that in place, now this paper gets quite interesting. And I will use this paper actually. It is a good time at this moment to read through the abstract and say, what is it trying to say? What it says is, we present DeepSeek-OCR as an initial investigation into and this part is important. This paper is a proof of concept. It is not trying to achieve a state of the art in deep. It's an idea. It's a thing. They played with something and they showed that it works. as an initial investigation into the feasibility of compressing long contexts via optical 2D maps. Optical 2D maps is a fancy way of saying you just write the words on a page and now it becomes an image. Right? So DeepSeek-OCR consists of two components, encoder and DeepSeek blah 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 as the decoder. Now remember guys that when you use an encoders typically are bidirectional. Because they are bidirectional, everything is paying attention to everything. So, but while that, you'd say that, well, that's alarming. Now we can have, suppose on a page, we have hundreds of patches or thousands of patches, and they will all be paying attention to each other. So that brings us to one topic that I mentioned right now. Inside SAM, one of the lesser observed innovations was windowed attention. What it said is that if you have a patch, bucketize the patches into neighborhoods or windows. Right? This neighborhood, the next neighborhood of patches, the next neighborhood of patches, and let attention, self-attention, happen only within the window. Right? So suppose you have 1,000 patches, but you take a window size, I'll just take a very simple window size. Let's say that we take a window size of 50. Right? So you have 20 different windows. And within a window, the quadratic addition is only 50 square, which is a lot less. And 50 square times 20 is still like a much smaller number than 1,000 square. Right? So that Sam actually did that as one of the innovations internally. But it will come to it. The reason I mention it is that it is important and it will come downstream. DeepSeek-OCR consists of two components, deep encoder and a decoder, which is a mixture of experts model. Actually, the surprising thing is both of these models are by the standard of modern LLMs. Both of these are actually very small models, very, very small models. So, and they managed to achieve something with very small models. Again, this is a research effort. Specifically, deep encoder serves as the core engine designed to maintain low activations under high resolution input while achieving high compression ratios to ensure an optimal and manageable number of vision tokens. That's a long sentence, and let's decode it. So what they're saying is that the meat of the matter is in the deep encoder. That's the real deep. After that, the decoder is a standard measure of experts decoder. One simple way of thinking of decoder is just think of an LLM, a small LLM. And but they are saying that the deep encoder is the real deep. It designed to maintain low activations. By low activations means the number of parameters that get triggered is low, which is automatically true because encoders tend to be much, much smaller than decoders these days, or smaller than LLMs. And it can maintain like a VIT or SAM, they can maintain, you can work with fairly small sizes, even when the image resolution is quite high. So that's all they're able to do. Then they are saying it achieving high compression ratios to ensure optimal and manageable number of vision. So what they're saying is, see, when you convert 1,000 words into one page, and let us say for the sake of argument that you can take the page and make it only 64 patches or 100 patches. Let's say 100 patches. So what have we achieved? We have 100 visual tokens that are replacing 1,000 word tokens. Guys, does that make sense? A typical line will have about 20 tokens, 50 lines on a page. That's about 1,000 tokens. And you have reduced 1,000 tokens, word tokens, into just maybe 64, maybe 100 visual tokens. So you have a massive compression in the number of tokens. Why is the number of tokens compression useful? Because of the quadratic attention, right? Cost and attention. So then they go on to say that experiments show that when the number of text tokens is within 10 times that of the vision tokens, that is the compression ratio is less than 10x, the model can achieve decoding OCR precision of 97%. So what they're saying is, if you take a page on which you have written text and you try to pass it through this system, and you give it a very simple task, you're not even asking it questions, you just say reproduce this thing for me again. That is the OCR thing. Right? It is able to, the accuracy that it achieves is 97%. Sorry, precision of 97%. It gets everything practically right. That's what it says. And even though it has achieved 10x compression, and we'll see it in the paper a little bit. Even at compression ratio of 2x, the accuracy will still remain at about 60%. Now, 60% accuracy in OCR is actually not terribly good, but 97% is really impressive. This shows considerable promise, but why 60% could be useful? Let us imagine that you have a context window that is 32K, and you are going to feed in document that is 20 times that. In the normal way, you wouldn't have been able to feed it into a large language model with 32K context window. Right? So on the other hand, if you go through this technology, you can compress a 20 times larger document into it. So it's a feasibility. So you may say, hey, at least it's possible, even though we take a little bit of a hit on accuracy, it is at least possible to feed the large context into it, which otherwise would not have been possible. So they go on to say that this shows considerable promise for research areas. Such as historical long context compression, that is, long past conversations and so forth, and memory forgetting mechanisms. So this memory forgetting mechanism merits a little bit of a discussion. See, human memory is sort of abstracted. We remember what happened today very well, what happened yesterday less well, what happened a month ago, we remember in broad strokes. But right, what happened last year in even broader strokes. So there is a process of forgetting and remembering only the semantically relevant parts from the past. And so they will talk about in this paper a way to forget or not pay attention to past things as much. Beyond this, DeepSeek-OCR also demonstrates high practical value, and then there are benchmarks that show it's very well. Now, one of the lovely things is that even if you treat it as a pure OCR tool, it tends to achieve very, very good performance, right? With very low token utilization. This Y scale, let me just zoom out in this picture actually. I wish they had made the picture separately, not put two pictures on the same page, same side by side, just to show what is going on. Look at it. Most models, let's say intern V2, a pretty impressive model. The number of visual tokens it does is 7,000. That's a lot of tokens it uses to understand what's written on a page and then to extract information from the page. Right? And these models do achieve a fairly good state-of-the-art. Right? There is a Quen encoder series model which achieves an even greater state-of-the-art. But look at where, from an efficiency perspective, that's why the scale is. You notice that this is 7,000 and this is just 100 tokens. So the reason the scale is inverted is because what they want to show is that efficiency increases. If I can read the page into lesser number of tokens or patches, then obviously I'm having a very high compression ratio. Right? I'm having a very efficient process. But so the DeepSeek-OCR, you notice that they all stride here. What they are is very few tokens they use relative to the state-of-the-art OCR models. But even with that low token utilization, they achieve pretty state-of-the-art results. Right? So that is what they're trying to say. And here also they are trying to say that text tokens in per page, depending upon how much text tokens you put, you achieve a very high compression ratio. You can achieve, like for example, this is just a compression ratio charts and so on and so forth. And they have, as we'll see, they have different slicing techniques we'll talk about. Anyway, so this is the main result of the paper. Now, how do they do that? That's the whole question. And I would like to quickly go through the architecture that they do. So this is how they do it. And it's quite lovely, actually, what they are doing. So they are saying that, see, let us say that you have text, and the text is sitting here. You have converted it into an image. Now, we just talked about it. You can feed it into VIT data, all of these technologies, and what you will end up with is basically downsampled, reduced pictures that you can feed into an LLM. Okay? But this is a typical way people do that. Now, the way these people suggest doing that is different. They are saying, we will, so this, by the way, guys, all of you must be familiar with. For example, describe this image. What will you do? You will put it through an encoder, then you pass it through a, for example, think lava. Right? Does this look like lava, isn't it? Something like that. Right? So, but now, let's look at something like this. What is their contribution? Their main contribution is this, and I'll just highlight this box. This is their main thing, architecture. The rest of it, like the decoder, DeepSeek, a 3 billion large language model that they use, those are straightforward. I mean, in the sense that they get away with a very small language model. Right? And so the first thing to note is that, so when you look at this picture, let's observe some things very carefully here. First things we observe is that somewhere there was text. Of course, there was some text. Sorry, this is so fat. Let me make it tiny. Text. Texts somehow became an image. Well, in this particular case, they literally took a page from a research paper. Now, normally this is, if you're familiar with vision models, VITs, you see the standard 16 by 16 patches. So you'll break up the page into n number of those patches. Those patches will go into your SAM VIT. What will come out? You will get contextualized tokens. What they do, and this is very interesting actually what they do, they downsample and they use a convolutional neural net. And I don't know, somewhere they mentioned they use 2 layers. They use 2 layers. Now, if you remember, what does convolutional filter do? Whenever you use a convolutional layer, because of the pooling and so forth, you always end up downsampling, right? So now what has happened is you had patches this big, and now they have become even smaller patches, right? And when they have become that, you take all these vision tokens. Now that you have vision tokens, imagine what happens when you put it through CLIP. Just as a recollection, CLIP is, you remember what CLIP is, guys? CLIP is your contrastive loss vision image pre-training. What does it produce? What CLIP produces, in technical terms, why would I want to pass it through CLIP? See, each of these patches, they have observed the other patches. So they have all gotten contextualized, right? So they have had their windowed attention and they're contextually rich within the window. But what they don't have is global information, because in this process, they could pay attention only within the window, a window of patches, isn't it? They couldn't pay attention outside the window. So now, when you pass it through a CLIP, just remember that CLIP is essentially another VIT kind of model, but which has been trained with contrastive loss. What is the core goal of CLIP? To create a semantic embedding of that image, isn't it? To create a good semantic, it will extract the semantics of that image into a vector form, right? And so that is why you have the word global attention, right? And local attention comes because of windowed attention. It's one of those things inside SAM. So then what happens is, so that I hope explains everything. Local attention, downsampling using a convolutional neural net. So you have a 16x compression right off the bat, right? Downsizing, 16x downsizing right away of the image patch. But then you get those vision tokens and you pass it to CLIP to come up with a global understanding, a global vectors for this. Then what you do, and then the rest is easy sailing after that. The rest, what they say is, now we are going to feed this into what? We are going to feed this. And by the way, notice that there is a residual bridge here. What does that mean? We are not only going to send the vision tokens, but we are also sending a globally enriched token. A clip produces the global attention, right? So you're not letting go of the those vision tokens that were local. These things came out of SAM, but you're also adding to it, because that is this operation. You're concatenating also the clip token, the global information, and then you're passing it in. So at this moment, if you look at the journey of image through this, the general feeling we'll get is that it is a process, or what I would call as, it is very rich in the semantic information of the page, isn't it? That's what Clip does. That's what Sam does. They all are very good at picking out the pictures, the locations, the boundaries, and so on and so forth. So all of that rich derivations from the image is now flowing into the large language model, right? Which is a mixture of experts model, the decoder, they call it the decoder, which is another synonym. Yeah, I think of it as an LLM, if you want to have a simpler idea. But what is also happening is a user prompt. The user prompt, in the simplest case, could be reproduce the image, right? Decode into the original image, right? Or it could be a question about that image. It could say, what does this equation mean, or something like that, and then you would end up doing this. So if you compare it to, now when you look at this picture, you say, okay, this looks very good, but the highlighted part is innovative, but other than that, for example, does it not look somewhat like lava, or one of those blip2 and those kinds of models? Any vision language understanding model, multimodal model, in which from one direction vision tokens go in, from another direction text tokens go in, and they go into a LLM, into a decoder, and then you can ask it questions and it will say something about the image, right? So we are all familiar with that. So where exactly is the innovation? And so the key innovation is in two ideas. First, let's convert text, some text, not all of the text, some text into image, and then pass it through the image pipe, and have another parallel channel for the other text. So you say, now what in the world are we doing? Why are we taking this big text, right, passing one part through, imagifying it and going through this convoluted route, putting it through SAM models, then putting it through CLIP, and then finally coming out with a whole bunch of vision tokens. And then in the other channel, we have prompt. So the way they say it is actually quite interesting. They say that, see, suppose you have a conversational context. The user says, at the end of the conversation is going, and so therefore, it says, so should I, in view of all this, buy the smaller router or the bigger router, right? Now you realize that this question cannot be answered without the historical context, without all that has been discussed. But what has been discussed may be a mile-long conversation in which the user might have also told what he or she has been cooking that day, a lot of irrelevant information, right? And all that information, and this is a problem in chatbots, right? If you keep the richer the context you make, the bigger it gets. The bigger it gets, well, if you could somehow squeeze it into the model, advantage is, well, you can now give really very meaningful answers. You become the fellow's best friend answering him, because you know all about that friend, about that user. On the other hand, the compute cost goes up and it may not fit into your context window at all. So what we are really saying is, case by case, like what you do is what the user is saying now, recent part of it, what the user is asking, put it in the text channel, let it be the prompt. But the whole history that you have that will enrich that question that the user has asked, and that you can use, think of it as the thing that you would, in quotes, rag, right? What you do is imagify it, right, and pass it through the vision channel. Are you getting that? And that's the beautiful thing, because that can go through compression. Now, one of the things that they say, which is even more beautiful, is they're saying that, see, there should be a recency bias. So what you can do is the conversation you had with the user in the last 1 hour is probably more relevant than the conversation you had yesterday, which itself is more relevant than the conversation 1 year ago. So what you can do is, because you are imagifying this past conversational history, you can be clever. What you can do is things in the distant past, you can make very low resolution images out of it, right? So there, lots of text will just produce maybe 10 tokens, right, or 20 tokens. But recent conversation produce lots of visual tokens. So you see the cleverness of the idea here. What you're basically saying is there is an inverse, there's a huge recency bias. Recent conversation, look at it at high resolution in the image, right? Make it high resolution images. But as you go deeper and deeper into the history, then what you do is shrink those. Don't give so much space, so many tokens to distant past conversations, right? And so that's the idea they're promoting. And what they're saying is, if you feed this in now, you get an output. That's the core. And the amazing thing is that it does work. And the way it works is, and the way I look at it is, my own feeling is, after reading this paper, first of all, it uses the OCR technique, but has very little to do with OCR. Its primary goal is not OCR. It is context window compression, right? Pushing more things into the context. And the second thing is, it brings about massive efficiencies into the compute process, which is one of the primary goals of DeepSeek. But there are actually two more benefits that accrue from it, or rather one more benefit. They call it deep parsing. What happens is, let us say that they see a picture, right? Now think lava style. You can give it a picture and ask it to explain it, caption it, right? What happens is, when it sees a picture and you say, picture in, what out, you can actually train it to not produce just a picture, but picture with a really good caption, with more. So what happens, or another way that I think about it is a semantic augmentation framework. This whole architecture is a semantic augmentation framework. What you put in and what you get out. What you get out has more information than what you put in, right? Which is the most, I think, this paper's main contribution when the dust settles, in my view, will be recognized as the fact that you get this benefit. Information out is greater than information that went in. Right? Despite all the compression and everything, actually you get more out of it, right? Surprisingly, because all of these pieces, it's almost like in the journey there are all these powerful elements sitting. There is SAM sitting, right? There's convolutional sitting. There is clip sitting. They are all trying to understand that picture in globally, locally, and in so many ways. They're trying to get it. And so you end up with, and so I'll use a new word of my own. This is my word, by the way. I'll call it semantic augmentation. What they have created is a semantic augmentation framework. Right? What goes out is more than what goes in. And that's the most remarkable thing. Right? And so they call it the deep parser. Deep parser. It's really very good, actually. So let's look at the encoder, which is the core thing. What is the encoder made up of? Very basic. You have to do patching. So now what they have is, one of the lovely things they have is multi-resolution support. Remember we said that you can have things at many resolutions. So you can have it at tiny resolution, small, base, large, but they also support, besides this, a dynamic resolution, right? Which they call the Gundam, after the anime character Gundam resolution. So what they do is, let us say that you have 640 tiles. Tiles is, by the way, a window size into which certain number of patches are there. So now local views of the image. So local views, local view of the image, and you have n of those. And what they are saying is, so those are small local views, very high resolution views. But then zoom out of the picture, right? And take a low resolution but global view of the picture, right? so that you capture global information. So I don't know, guys, if you think about it, it is doing something that UNet used to do. Remember, UNet has, like, in it, as you would go down the filters and then deconvolute up, somewhere along the way, you would gain global information but lose local information. Like locality would be lost. And so by putting the short circuits in the UNet, you would preserve both the local and the global understanding. And so this tries to do something similar to that, but using a different mechanism. And so that's the resolution part. The decoder part is very straightforward. There's absolutely nothing. Just think of an LLM. They're using a mixture of experts. What is most remarkable is what a tiny model they are using. It's just surprisingly tiny. They take a 3 billion parameter model, and the actual activation is that of only 500 million parameter, right? The efficiency, the inference efficiency of a 500 million small model, because they are using a mixture of experts, right? So they have about 570 activated parameters. So very, very small models they use. So now let's look at this. How do they do it? Like, how do you train a machine like this to behave and to become so good? So we will just carefully analyze this image, just one part of this image, and I think that will tell us all. See, what they do is, so this is, I'll put a line here, and let's look at it. You see a figure here, a diagram here, right? So let's look at this, 2 NIC. So first thing you observe, let's observe this line. What you see is, it is giving you guys, can you guess what this is? What this part is? Detected. You're detecting something. The location you're detecting it at. From here, you're giving you the bounding box, isn't it, guys? Right? It is saying, I am detecting a text at this bounding box, and the text is this, right? And then more bounding boxes and so on and so forth. And then it says, let's say, here is another, there is an image here. What is this image? It is this image here. It detects an image, and this is the size of the image, right? The bounding box around the image. It is detecting. And then it moves on to say, I also see text here at this location, that is this location here, and from here to here. And then it goes on and gives the text. So if you notice, this here is here. Right? Do you see that, guys? How it is doing? So what it is doing is, it is converting it into a HTML-like markup, right? You're forcing the machine to understand an image and convert it to a markup language. The difference is, unlike, like if you, those of you who remember, a lot of the models have tried this in the past, but this one, where it benefits from is that it preserves locational information, right? See, if you have to reconstruct an image, you better have the positional information, isn't it? So it preserves the positional information, and then it goes on and on and on, right? And then you would agree that the way, if a machine can do something like this, it's doing a pretty good job. If you can train it to reproduce it like this, it is doing a pretty good job. And it is effective OCR, though not a traditional OCR, isn't it? It's sort of an effective behaving like an OCR, yeah, right? And that's what it is. They train it with a lot of data. And one of the lovely consequences that they have of this is, look at this. You give it a chart. So maybe I need to zoom even more into this. Let me do that, because in this, one thing about this paper is the figures are a bit too small. So guys, if you look at this image, look at this image. What is it? It's a chart, right? Now, observe carefully what it has done. It's just something very amazing it has done. This is obviously the data that it has extracted from it. It's basically saying that I can represent the data as a table, isn't it? And if you try to render the data, it will become this. which is very, very nice because as you can see here, this is here. Where is that? Here, right? It is here and so forth. So everything comes out correctly. Then they say, let's look at the, again, so you feed it data like this. What are you doing? You're telling it that there is a chart, but understand the chart like this as a table. So what it will happen is every time it sees a chart, it will automatically learn to convert it into a table. Right? It is also trained into geometry. 1 second. Like when you see an image, what it does, it basically it is almost like a SVG kind of a, but they have done it as a JSON, but something like SVG, a rendering of the locations through lines and polygons. It has kept it as an image. Yeah, go ahead.
Yeah, so this poses a very important application, especially for getting a understanding of the data sheets of the specs, like right. Especially when you have clock signals and complex timing diagrams. If it is understood with markers, then nothing like it.
Yes, exactly. So this really opens up. That's why I call that to me the most important contribution of the paper. Like first of all, it is not about OCR.
Yeah, right? Exactly.
That was just accent. Most people they realized that and they said, oh, you know what? This does magic with context windows. Now you can massive compression. You can shove much more into the context window, and you can get compute efficiency. So those two things. But the thing that I remarked there, and I think many people missed, is that I also see it as a semantic augmentation framework, isn't it? What comes out of it is much more than what went into it, right? And isn't that amazing? Right? It just adds annotations, lovely things to it. And so that is it. And the data engine. So the rest of it is the mechanics of it. Let me see if any figure merits for that. But one of the things is, look at it. At vision token 100, right, which is about a 10x compression. Look at the recovery, OCR recovery. Even if you treat it as a dumb OCR engine, it's not doing bad at all, isn't it? You recover most of your tokens pretty well. Right? So now you would say, well, 7 pages it recovers pretty well. Now you say that, well, I'm not happy with 98.5%. I want 100%. Because when you put it into the context window, into an LLM, everything goes in. The trouble is, does the LLM actually look at all the tokens? Right? There is the problem of context rot. When you shove in a lot of tokens into it, it basically also begins to feel, where am I? Right? So you might as well. And the other thing is, you would rather send an encyclopedia in that context window, somehow shove it in as an image, than not be able to send the encyclopedia at all. Right? So that's the main value that this thing brings. And it's very exciting, actually. It's a very nice paper. And but even as a basic reconstruction, it's not doing badly. You notice that this is the SAM quality, right? It makes lovely bounding boxes, right? It knows the objectness, that this page is made up of many objects, the text object, this object, the table object, etc., etc. And that segmentation ability is coming from the SAM side, right? Then this is interesting. See, if you take an input image, look at this input image. We'll just look at this image here. This image, data point, Europe, etc. Data point. Now, let's pay attention to just this. You have an input image here, and here is a deep parsing of that image. What did you end up with? You ended up with the image and a table with it.
Yep.
Right? Yeah. It's lovely, isn't it? Yeah. And then they say that if you want to just reconstruct it, just treat it as a dumb OCR exercise, then also it's not doing badly, isn't it? Compare it with, if you just look at this particular region, let's zoom in. Actually, in this paper, the problem is the zoom in is a little bit not. Okay, so here we go. Let's zoom in only to the Europe part. Even more zoom in. I can't zoom in anymore. So look at the Europe part. Latest GS proprietary data, major changes in view, right? We recently raised blah, 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 etc., data point, blah, 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 etc. And look at this. It has pretty much gotten all of it, isn't it? The formatting has changed. So I suppose that's what they mean, that they lose a little bit on the OCR. Formatting has slightly changed, but it's come out, the content has come out well. So the way I look at it is that it's basically a semantic transduction and augmentation framework. The semantics filters through very well, right? Passes through very well through this machinery, in spite of the massive compression that it brings about. And that is the paper. That's the fun part of this paper, right? And it goes on to, like, let's look at this image, then it puts a whole interpretation here, right? You see that deep parsing, it will give a full interpretation. Like this was the image. Research is widely recommended, etc. So that is all right. The rest of it is in a community of practice. So in a community of practice, so it recovers the text, but it has changed the formatting, right? But look at the additional thing. It looked at the picture and it threw an interpretation to it. Right? Sometimes you don't, like, people write images, like in technical documentation, so often somebody will throw an image without explanation and assume that you understood it.
Which the deep parsing is done by the
DeepSeek-OCR engine. Right? Isn't it lovely that the whole system ultimately comes up with more?
Yeah.
Right? And that is it. And just they give example after example.
Oh wow! Yeah.
Yeah.
Chemical composition.
Yeah, it understands chemistry and it even writes it in the SMILE notation. You know, the chemical formula notation, right? And how neat it is. Actually, sometimes it's neater. So look at the deep parsing. Look at the like OCR part, the rendering part. This looks like this, right? Except for this image, it does look like this image. Would you agree? These do, like this image. Sorry, this image is the same as this image. It came out well, right? This image. On the other hand, look at what did the parsing do? Interestingly, this image here, it has inverted the location of F's. Do you notice that the chlorine oxygen molecule are down here? The fluoride molecule is up here. Fluoride atoms are up here, right? It is exactly the same. But why did this happen? Because it was reconstructing from the semantic information. So you can use it both for deep parsing and for rendering. It is sort of a dual purpose model. And so it goes on. The only part of the paper that I personally was a little bit, I felt was hand waving is this whole idea, figure 30, in which they said, hey, what we can do is the more that you go into the past, the blurrier we can make the image, right? Low resolution we can make the image. So the problem with that is directionally it's right, but obviously like as a person who comes from survival analysis, the persistence of the lifetime of things, right? I would have liked to, I mean, the right way is memory persists more like I happen to know, most people, that it follows more like a Weibull distribution, which is a flattened out exponential decay. It doesn't geometrically collapse like small like that. Right? It doesn't. So anyway, this is a first level paper. The other thing is that how do you deal with non-temporal axis? So you see, they have looked at the temporal axis, time axis. But the way I would look at it is along a relevance axis. See, when you give it a static document, encyclopedia, you can't say that the beginning part of the encyclopedia treated with blurry images and later part give it with high resolution images. So what you need, I think what should be done, and the directionally they can move to further work is they can take the user prompt, and for each section of the document, they can look at the embedding cosine similarity. So they will get the relevance. Which sections of this big encyclopedia are actually relevant to what the user is asking? Once you have come up with the relevance score for this sections, and then what you can do is you can predicate your resolution, visual token resolution, on the relevance. Things that are high relevance, zoom in. Things that are low resolution, zoom out. Right? So that could be one. Like it occurred to me as I was thinking through this paper, they could have done that, and of course you can compose these two ideas together, time axis and this thing. Time axis to me is clear that something like a Weibull distribution would have been significantly better. Maybe it's just a thought, but it's because I come from the survival analysis background. So that is that. That's a paper. Guys, you go ahead. Somebody, you ask me a question.
The human memory that you had mentioned earlier about forgetting mechanism.
Yes.
So is that what this?
Yeah, they're trying to do. They're trying to say that that forgettingness, right, gives you another compression axis. What you can do is
selectively,
historically, in the conversational chat, things that are very, very old, give it a low resolution image, blurry image, right? But it's a very like the way they have done it currently is a very geometric argument. Just downscale it, downscale, right? But you can be a little bit more nuanced because human memory, right? It doesn't fall down to zero. There's a persistence of semantically relevant things in our life that have happened. We remember. You remember, like for example, your child's birth, but you would have forgotten all other things that happened that day, isn't it? So there is a relevance aspect to it, and there are other distributions. Like for example, there's a whole field of survival analysis of what survives and what doesn't, and so forth. That obviously you can think that if somebody is can do extensions. All right, guys, that's all I have, and I'd like to let's open it up for discussion. If anybody would like to throw in some ideas.
There's a question on the chat.
Oh yes, sure. Question on the chat. Let's look at the question.
I think it's already answered.
Oh, okay. Nice. All right, guys. So this was the paper. I hope you had fun. Please do ask questions and let's have a discussion. Did you get the hang of it? Like what this paper is saying? Did you guys get a hang of it from this explanation?
Yeah, I think, at high level, I start to understood, but given this, my paper reading that I attended, I mean, I need to stitch together a lot of missing pieces.
Yeah, it sort of requires that you have background with SAM, VIT, CLIP, etc. Little bit of that background is essential. CNS is essential. But I hope I gave you the general flavor of it.
I mean, from little I know, what they're trying to do is similar to, text processing. You kind of tokenize it and then you'd, add like positional embedding and all that. I mean, so here.
No. I mean, that you do, that is the standard transformer. What these are doing is they have taken a detour.
But here they are taking the image and then breaking it into, like tokens, they are kind of creating the patches, right?
That's
and then they're kind of adding to it the clip player or whatever, which adds more information, right? Like similar to positional embeddings that you add to the text. I mean,
anybody else, guys? I see a lot of folks. Anybody has a question or anybody has a comment? Was it helpful? Or is there any part that you would want me to clarify or talk about? I felt that this is a very exciting paper. It's quite a breakthrough. And the fact that people took the unusual approach of converting text to images. I mean,
it's a very novel.
It's a very novel approach, right? And
the literal meaning of picture speak 1,000 words.
Yes, literally, the picture speaks 1,000 words. It's literally embodied in this research paper. It's a marvelous research paper. And actually, there's something peculiar. The month of September, October, these 2 months, it has been raining OCRs. Suddenly, there are lots and lots of OCR research papers. So when this paper came out, people thought, okay, yet another OCR paper. It took people some time to realize that actually this paper, while OCR is a technique it uses, it has nothing to do with, well, its main purpose is not OCR. It goes to the heart of how transformers work.
So this is this a so if we want to give it a spin, like
you can download it. It's a very small model.
Very small model, and probably
in fact they give you the code. They give you the code, and you can try it out. It's very, very easy. DeepSeek-OCR. And the people have created it now for all the GGF bundles, and all of that is there. Right? So you can download it so here's the thing. They give you all the instructions. See, learn this repo, which is easy. Right? Then if you use Conda, I use UV, but whatever equivalent, we use UV, as you know. And then bring it into VLLM, right, as an inference server, and just run it. There we go. After that, here is your code. What are we doing? Let's look at the code. What you do is you say, here's my model, enable prefix caching, don't do that. Some cache is, etc. Some basic things. Then here is an image 1, image 2, prompt, free OCR. In other words, just don't do anything, just convert it, do the OCR, right? And multimodal and sampling and blah, 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 the parameters, and then you see the output. So very easy to do, transformer inference, right? And if you use the transformer, the library, Hugging Face library, it gets even easier. You see how easy it becomes? This is the standard code we write with Hugging Face, isn't it? Just Hugging Face code, and then prompt, convert the document to Markdown. So that will be, the Markdown, it will produce your image, here the second, out you will get it. And so they have this different resolution modes, tiny, small, base, large, and then they also have this dynamic mode, the Gunda mode, which is, I believe, after any character. So this is it. This is the paper, guys. Well, all right. Thank you for being part of this meetup, all of you. Any questions, please? I'll still be here. You can ask. And I had fun, actually, reading this paper and presenting it. I hope you had some fun in listening to it too.